The human race has been exploring and conquering new territories on Earth for over 100,000 years. Unfortunately, as a result, the entire surface has been claimed, with many still hungry to spread their influence across new domains. As Neil Armstrong has said, "The conquest of space is the greatest adventure of our time." It is now time to bring forth a new age of space conquest, so that you too will be able to expand your dominion across the galaxy. Nuclear reactions are the most powerful source of energy and will be used in future space missions to explore and colonize new worlds in space. Nuclear fission is a type of nuclear reaction where a large atomic nucleus is struck by a neutron, splitting it into two smaller nuclei, releasing a tremendous amount of energy, and some neutrons to continue a chain reaction, as demonstrated by the balanced equation and diagram. This process has a high energy potential, with 1 gram of uranium generating as much electricity as 30 million kilograms of coal. Fission reactors have a wide variety of applications, which include rocket propulsion and energy production in space settlements. Nuclear thermal propulsion systems use nuclear fission reactions to propel fuel exhaust. This method is far more powerful and efficient than chemical thrusters that are commonly used in space missions. In fact, thermonuclear thrusters can accelerate for 6,700 seconds, while a rocket with chemical thrusters can only accelerate for 465 seconds. Thermonuclear thrusters won't be used while in the atmosphere due to the risk of a dirty explosion. The moon will be the first celestial body to be colonized because it is the closest body to Earth, taking around 3 days to travel to with our current technology. The moon also has a low escape velocity relative to Earth, which means that we can launch heavier payloads for a fraction of the price. There are also valuable minerals and resources that can be mined on the moon. Nuclear reactors to power the moon colony would be small and compact, so they are portable and cost-effective. And the tremendous power output produced by the reactors would be able to moderate the climate, support mining operations, and shield hazardous cosmic radiation. Space stations powered by nuclear energy would make great checkpoints between Earth and other destinations in the solar system. Nuclear reactions would be the only feasible energy source for space stations. Once a moon base and a space station have been established, colonizing Mars would likely be the next step. Rockets with thermonuclear engines would be able to quickly travel to Mars in 80 days, where chemical engines would take 320 days. Nuclear reactors on Mars would serve to protect the settlement from cosmic radiation and maintain the climate like the moon base. Since Mars is much further away than the moon, nuclear reactors would also assist with agriculture, since the colony can't rely as much on cargo loads. Nuclear reactions produce so much energy they can theoretically be used to terraform Mars from a cold, barren wasteland to a habitable planet like Earth. By using controlled nuclear reactions or explosions, we can release carbon dioxide from the surface into the atmosphere, heating the planet and contributing to global climate change. Rockets with thermonuclear engines would be powerful enough to transport valuable elements and molecules in the form of comets and meteorites towards the planet, which will eventually form new oceans that can support living organisms. The nuclear reactors would also be able to generate magnetic shields around Mars to protect the new atmosphere from the destructive cosmic radiation. Here is an interesting rate law equation to end things off. The half-life of uranium-235 is 703.8 million years. If a spacecraft traveling at the same speed as Voyager 2 takes 800,000 years to travel to Alpha Centauri, and a rod of uranium-235 is brought as a fuel source, assuming 100% of the fuel rod exists at the starting point, how much of the uranium will decay by the end of its journey? We find the rate constant by using the half-life equation. Now that we found the rate constant, we can use it to find percent left by using the first-order integrated rate law. Then we subtract percent left by 1 to get the percent decayed, showing that only 0.08% of the uranium has decayed after its long journey. In conclusion, nuclear chemistry will help us achieve our dream of one day exploring the solar system, colonizing the moon, and eventually Mars.